Good morning to everybody. Thank you for coming from so far away to something that had never been done before this year. The federal government has been giving funds to researchers in both academia and in practicing laboratories for quite some time. But for forensic science, we really are talking about a decade of research. Very commonly, research dollars would go to some place and they do the research and they publish it, and you'd hope to read it maybe if you had time to read the Journal of Forensic Sciences or Journal of Analytical Toxicology or wherever it got hidden. And maybe you could then apply it to your casework. NIJ saw this opportunity of, we're a little bit of a different federal agency because our recipients of that funded research are actually operating crime laboratorians doing examinations to help resolve cases. It's very unusual. You don't have time to double the research and make sure it actually fits your workload. You need to have someone come in and plug it into the wall and say, okay, it works now and it's been validated. Do your mini validation so you can use it in court and meet voir dire requirements so that you understand it. But you 12 bodies represent the country of examiners. And yes, we have 5 from Georgia, but Georgia's a nice state, so we hope that Georgia will spread it out around the areas you're at. Okay. We actually have, Georgia has 5, Illinois has 1, Colorado, California, New York has 3, 2 from the real place, the city, and 1 from upstate, Albany, and 1 from Florida, locally sort of. We're missing Texas this time, and with a president from there, I'm surprised that happened. You're the 3rd guinea pig in our 6 guinea pigs this year through NIJ's hands to do this technology transfer workshop series. A few critical things that you should know ahead of time. There's a signature form in your notebook in front of you. There's a nice white sheet, which kind of tells you who's here presenting this to you for 2 days and where they're from a little bit. Then there's a schedule, which is very colorful, which tells you what to expect or sleep through in the next couple of days. Right after the schedule is a signature form that allows us to actually videotape what's happening. This also is a guinea pig experiment by the federal government. A workshop like this, normally being invited to it, you become one of the few in the whole world that will get to contribute to the enhancement of the forensic services that we hope to gain through this workshop exercise. And you also become one of the lucky ones who gets to enjoy Florida, usually in the off season, but right now it's a little warm. You would have to then spread it through your own lab, spread it to people in your region, spread it through the regional forensics associations, maybe even at the academy. When you're talking around coffee, that's all you drink at the academy, I know. Maybe then you could kind of spread what you hear in these 2 days. The federal government's going to the next step and saying, what you are contributing in these 2 days will be enhancement of the technology in that the presentation team is going to tell you, here was this tool out there not being used in the forensic world to help with case resolutions. We're going to show you what we did on the research side that shows that it can definitely be used for certain applications in the forensic world. It makes our life better, better resolution of cases, better sensitivity, selectivity, less extraneous materials being taken forward through the forensic biology process. All excellent. You will then say, well, what about this? What about this? What about this? And they'll say, oh, we studied that and here's what we did. It may not be part of the formal presentation in the PowerPoints. We could just give everybody in the country the PowerPoints, but you will be interacting substantively to improve what we learn from this procedure to make the technology more applicable to forensic services. That's your role. You're representing the whole country, but we're capturing it digitally. It will then be an uploadable file that every forensic examiner who happens to be in a forensic biology component of their lab and needs laser microdissection, they'll now know, oh yeah, I'm going to watch that, and then they'll hear your question on the same topic they had, because we all think alike because we're all great forensic scientists, right? Wait, you think differently because you're from Georgia. But it's good, Georgia. You'll be contributing in a way that you'll be representing without having to later go out and say, here's what I heard, here's what I said, here's what I asked, here's what they said. That will all be digitally captured. If you hate your hairdo like I do, you'll see it on camera, unfortunately. There's a signature sheet in here that we have to collect as NFSTC under federal law. Has to make sure you know you're on camera, that it's being recorded, and that everything's okay with you to do that. The back of your head will be on camera a lot. The front of the heads will be on the presentation team, so they've already chosen the correct profile they want, left or right profile, with the lighting and so forth. Also, you're in microphoned areas, so when you speak, you don't have to yell. They're all wearing nice little headsets so they look like camera ready people, and they are. Luckily, David's camera ready much better than me because he has hair also. In the end, though, laser microdissection is our third and fourth workshop. The examiners are Monday, Tuesday this week. That's y'all. The forensic supervisors and technical leaders are coming Thursday, Friday for the same technical component of the presentation. They'll be talking also globally about the voir dire, Fry, Kumho, whatever state law you guys have to follow to get this thing accepted into court. They'll be talking about that a little bit. They'll also be talking about how do I use these 2 days of learning that I got as leverage to go get myself a laser microdissection device for my laboratory. We are very lucky that Leica Incorporated brought 2 laser microdissection 6000s with fluorescence attachments and have set them up in the NFSTC laboratory spaces in the building next door. You'll be there a lot. We're filming that stuff as well. Having one of those here is kind of a miracle. Having 2 is unbelievable. If your lab ever gets 2, that means somebody fell into money. Hopefully not you through your will. That would be, we'll leave that. So we're very lucky to have Dr. Andy North here as well. Leica donated the week of time on that instrument, and it's wicked great. You'll see the newest instrument, not the first generation, you're seeing second generation. Whoa. First generation, kind of like the research team, they used it, they said, you know, this thing doesn't work the way it's supposed to. They fixed it, and now Leica has fixed it too. So your team of presenters is showing you the latest technology and how to apply it to forensic services.
Well, thank you for being here. Just to let you know, the 3 of us and the whole team has basically pulled this thing together in the last few weeks. So you're going to be the guinea pigs. But I'm glad you can make it, and it looks like the curriculum's really come together. And we have a lot of material, and hopefully we can cover it all. So you're here to learn about laser microdissection. And I kind of put this little introductory slide up here that the primary reason I think most of you are here is to use laser microdissection to recover sperm cells in mixtures. So I've got here a picture of a mixture on the left, and this is actually from the computer screen of the software. And on the right is actually after some dissection of sperm cells and epithelial cells. And the idea is, of course, to analyze these cells for DNA analysis. So basically, we're going to have 3 instructors, and we're also going to have Andy Lee from Leica Microsystems to help us out technically. And I'm Christine Sanders, and to tell you a little bit about my background is that I worked for LAPD starting in 1991, and I worked for them for about 10 or 11 years in their serology DNA unit. And so I come from originally RFLP background and the evolution of PCR and then STRs. And after about 10 years, I moved to Chicago, and where my husband was going to medical school, and decided to go into research instead. And I first went into neuroscience research, but I still had the forensic bug. So I applied for a grant with NIJ, and that's what made me eventually come here. I got the grant to research laser microdissection and its applicability to separation of sperm cells from epithelial sperm mixtures. So I was at Chicago Medical School, and we did that for a couple of years, and then now I live in Pittsburgh. And basically now I no longer work for Chicago Medical School. I'm pretty much a consultant and a full-time mom, and do things like this and work for Duquesne University a little bit doing some teaching. And I'm going to have Pat and Kelly introduce themselves so that you want to, Kelly.
Hi, my name is Kelly Reilly, and I'll tell you a little bit about my background. I actually spent 6 years at the Office of the Chief Medical Examiner in New York City. I started there in 1997, and so that's kind of how I got my start out of graduate school. And then after spending 6 years there, I decided it was time to move on. Had been September 11th, and I'm actually from a small town, and I said, you know what, I think it's time for me to move on now. And then I ended up taking a job, believe it or not, in Shreveport, Louisiana at the North Louisiana Criminalistics Laboratory. And that's where I am now. And what got me interested in laser microdissection was actually Christine. In 2004, I went to the American Academy meeting in Dallas. And that was pretty much fresh off of coming from the OCME, where there was a large volume of casework, and there was always a how can we do this faster. And when I came to the North Louisiana Crime Lab, they were still doing differentials using organics, organic extraction. And I said, oh my God, this takes forever, So what could we do to, we were actually had been talking about, well, what could we do to speed up differentials? Because of course, just like most crime labs, we have a lot of sexual assault type cases. And so I went to the academy meeting, and there was this presentation that I said, oh, this sounds interesting about laser microdissection. And I went to Christine's talk, and I said, wow, this seems like it could be great, and talked to her. And then luckily my boss, Dr. Pat Wojtkiewicz, is very flexible and open-minded when doing research because he loves research. And so I went back to the lab, and he actually asked me about it. He said, did you hear about this laser microdissection? I said, actually, yes, I did go to the talk, and I had asked Christine some questions after the talk, and he said, I think we should get it, because we had a meeting with the DNA section, and we said we need something that will, help speed up this process of doing sexual assault evidence. And so we purchased a Leica microscope in November of 2004, and since about January of 2005, I've been working on our laser microscope, and we're real close to putting it on the casework, so hopefully we can give you some good information. So that's why I'm here.
And I am Pat Wojtkiewicz, I think the oldest in the forensic science field around here. This is my 30th year in forensic science. I started in '77. And if anyone wants to know any histories of doing ABO blood typing or polymorphic proteins or where all these screening tests came from before we had anything like P30 and other things like that, you can ask me. I can give you a little historical lecture. But I really do like to keep up with new things. As Kelly said, I'm very oriented towards research. We've done quite a bit of work at the North Louisiana Crime Lab on new techniques and keeping state-of-the-art techniques. As I said, I've been there for 30 years. We've done a lot of new work there. I really like this type of microscopy. I also have some academic background. I teach some at the local university. And these microscope and microbiology has always been a love of mine. I really do enjoy microscopes. I had a great fortune in the 80s to work with probably one of the greatest microscopists in the world, Walter McCrone. And he taught me a lot about polarized light microscopy, forensic microscopy. We even had people come in and do drug analysis by microscopy, even when that was not able to be done or could easily be done by instrumental techniques. We were using crystal techniques to do some of the work. In fact, now some of the drug chemistry is done with crystal techniques. I really enjoy this work. Some of the things that we've done with the microscope you'll see tomorrow, the new fluorescent techniques, some of the chromosome painting, sperm painting are all part of this technique, and I think it's going to be a really, really good technique, which is really going to take you guys to open your minds to how this can really go into forensic science. Kelly and I have sat there and talked about it for the longest times, where if you look at some of these new processes, how you can take the whole sexual assault process and apply this microscope to it. And again, if you have any questions or anything like that, just pull me to the side or ask in the class and see what's going on. But I'm really looking forward to talking about some of the techniques that we've been doing at the North Louisiana Crime Lab with this microscope.
Pat, I'm glad to hear that about your microscope skills, because one thing I think as DNA analysts, and I think most of you are in an astrology DNA unit, is that a lot of us have kind of become rusty on some of our microscope skills, and this is actually a technique that you might have to brush up on your microscope skills. So where are we? Well, you pretty much know by now, you're in Largo, Florida. This is the first time I've been here, and you're at NFSTC. If you didn't notice, there is a link if you wanted to even know more about NFSTC. That was what I used to find out more about this place, and they also had an interesting virtual tour. We're not going to go on the walking tour. I kind of added that in. I wasn't sure the layout and what we were going to do, but you will actually, we'll probably, when we go to the lab, they'll show you some things and where all the facilities are that you need. Okay, so I just want to go over a little bit on the agenda. You'll see it's in the second page, starts the agenda. And so in the morning, Pat will basically talk about the basics of laser microdissection. And then we'll go on to if you know, if you need a little review, basic cell identification of sperm and epithelial cells. And then what you'll notice is that we'll have to go into the lab fairly early. I apologize for that. You may feel like you're rushed into the lab and you haven't really had all the background yet. The reason why we have to do that is because we need to get our samples to NFSTC staff to do the DNA work. So that we're kind of going into the lab a little bit early, and tomorrow there'll actually be a lot more theory and lecture. So basically you go into the lab, and then we'll demonstrate laser microdissection and give you instruction on it, and then you'll actually have exercises where you'll be collecting samples yourself. And then NFSTC, they will actually be doing all the PCR, the extraction PCR and the capillary electrophoresis, and then voila, tomorrow you'll be able to see your data. You wish you had that all the time, huh? And then, again, tomorrow on the next page, you'll see that there's a lot of discussion on both the research that both of my lab and the Louisiana lab have done, and some more advanced things like fluorescence. And then we do spend a little time in the lab looking at fluorescent slides, because it's a bit of an advanced option. And also this AVC software, Andy Lee will be showing this new software that will auto-recognize, hopefully, sperm. We'll see. It's kind of in a test mode right now. Okay, and I'm sorry, this is the day 2. Oh, and just so you know, your class is slightly different than the one that's going to be in a couple of days. The one that's going to be in a couple of days, we took out some of the laboratory work and we added a little more discussion time to talk about things like admissibility and validation, things like that. And you will actually be preparing some of their slides that they will be using. So when you're preparing your slides, if you notice, you're going to be preparing like double the amount, but you're only going to be using half of it. Okay, so let's just jump right into the first lecture. Does anyone have any questions?
As I said before, my name is Pat Voitkevitz. When I'm talking, just feel free to raise your hand or wave it if I don't see it too well. I can't see past about 3 or 4 feet, so it's a little tough sometimes. But just raise your hand or make a noise or something, and or if I start going too fast, we have in my classes sometimes I have the grunters. I start lecturing too fast, but people can't write. They kind of, I say, okay, it's time to slow down a little bit. But most of my talk is really just, this initial talk is really just about some basic microscopy. Some of the things about lasers, I know if you're in biology, you probably had microbiology, so you at least showed you a microscope. You learned how to look through it, at least to the point that you could think you saw what they were talking about, the instructor. Some people may have had more microscopy than others, but I just want to go a little bit of basic information about the microscope, basic information about lasers. I know in biology we probably have not had very much about lasers. So I'm going to talk a little bit about that, how this effect works there. I had a really good resource on lasers. My son has his PhD in fast pulse lasers, so I asked him about the information, and of course what he sent me was like about leveled here. I said, this is biologist, let's keep it simple. And so I weeded out and I got it down to, I think, a fairly simple stage there with information that what we need to know about lasers and not all the theory of how lasers make the light and whatever else. The first slide is the basic microscope. Most of you have seen the microscope. You've probably had at least some point some identification or some indication of where the parts are. Probably one of the most important parts that I think on there are your objectives. I'll go over that a little bit more because that's where the real power of the microscope is. You have the oculars, the body, the nose piece, the revolving nose piece, the stage. Substage condenser is important. This is one of the things that helps a lot towards making the resolution of the microscope, how you can get your ability to see fine detail. You have the fine and coarse adjustment. Now with the new Leica microscope, you just have little knobs to turn. These microscopes these days are really, really neat. I mean, it's like getting a toy to play with, looking at a screen up there as opposed to bending your back over the microscope for hours. It's really, really neat the way these are. But this is just a slide that shows you the basics of the microscope, where everything is located. And I'm going to go over a little bit of the points of what's important about the microscopes and how they work and things like that with them. If we look at terminology, just some basic terminology, magnification, that's the apparent increase in size of the object is based upon the microscope's objective, ocular, and body tube. Now, everyone says, okay, I'm looking at 100x objective, or 100x magnification, or 400x magnification. When you're looking at the screen, you don't have any idea of what magnification you're looking at. You may be using the 10x objective, but is it going through a 10x ocular? And by the time you increase the size on the screen, how much more magnification is it? So a lot of times it really doesn't say a whole lot when you say, yeah, I'm looking at it 100x, because it really doesn't tell you the true magnification of what you're seeing on the screen. It's more important when you're giving magnification of what you're looking at, say I'm using the 50 or 40x objective or the 20x objective, because that tells a microscopist really what the resolution or what you're looking at, or what kind of resolution you would be expecting. Whereas if you say, okay, I'm looking at 100x, well, that may be true. You maybe think you're looking at 100x, but on that monitor that you're looking at, it's not 100x. And if you put it on a picture after you've magnified it 4 more times, it's not 100x. But the resolution, or the ability to see detail in there, is what you're going to be able to tell, and you're going to get that from the objective. So really, in the most part, when you're talking about what you're looking at, say I'm using the 50 or 63x objective, or the 40x objective, or the 10x objective, because that's really tells where your resolution is and the ultimate magnification. Because you can take a 10x objective or a picture of that and blow it up to where it would be 630x or something like that, which you would have your 10x objective. Refraction. This is a change in direction of the velocity of the light as it passes onto one medium from another. This is part of your refractive index. This is what gives objects their appearance. If there was no change in refractive index, you wouldn't see any change there. What you're hoping is when that light goes through that sample, it bends because of the change in the medium, a change in the appearance. It bends the light. Actually, what it does is most people think the light just stops at those levels. It doesn't. It's just bent. It's bent out of the ability to pick it up. So that's why you see dark areas, not because the light has been stopped, but because it's been bent out of the aperture of the microscope. This refractive index is important because, again, that gives the ability to see things. It also gives the ability of alternative light sources or illumination to where you can see objects without having to do staining. That's what staining is actually done for, is to increase the contrast by increasing the refractive index. Illumination, method of illuminating or applying light to the sample. The 2 types of illumination that we're going to be looking at or thinking about is color illumination. This is one of the best illuminations there are. It requires a substage condenser, and what you want is the light to be going parallel through the sample. You see other types of where you have critical illumination where it's going at an angle, but color illumination is neat because it really gives the light is basically going through a parallel cone through the sample, and it really gives you really nice, bright illumination. Unfortunately, when you get to something like a microscope, when you have to stick that tube, the PCR tube, in the light path, that really messes up color illumination. The other type of illumination when we're talking about fluorescence is epi-illumination or vertical illumination, where the light or the excitation wavelength is brought down from the top of the sample. Some people call this incident light illumination, epi-illumination, vertical illumination, top illumination. They're not all identical, but in terms of just talking about where the light is coming from, epi, vertical illumination is the best description of that, or is a useful term. In the bright field illumination or bright field, the light source is focused through the sample and collected by the objective lens. And here's just a cartoon or cartography of bright field illumination. Your source is at the bottom, goes up through the specimen, or you see the substage condenser, which gives you the parallel light, and that's basically a color illumination. And then it goes up through the specimen where it's collected by the objective, and you visualize it through the ocular lenses into the eye and the retina. Over to the right, there's another little graph or a little picture that shows how the image or how a specimen would block it. In actuality, that light source, when it comes from there, is actually going to be diverted over here so that now you don't pick it up in the objective. That's why you see a dark area there. Some things, certainly opaque things that are really dark, like a piece of metal or something like that, will actually block the light. Actually, the refracting is so great that it turns it almost around, backscatters it in a way. But for most of these cells, they're fairly transparent. But what we're seeing is that light being refracted or bent. And the best example of refraction is, you've probably seen this 1,000 times by now, is the pencil sticking in a glass of water where it seems like it's broken. That's just the refraction of the light. And that's what's happening as this light goes through the sample. It's being bent, and as I show, it's being bent out of the area of being collected. And it may be bent more or less depending on the refractive index. And that difference in refraction will become paramount in different types of illumination when we get to a different type of illumination. Specimen refracts the light which bends out of the collection angle or the aperture of the objective. An objective lens's most important part of the microscope. When you're looking at purchasing a microscope, don't spare the dollars on the objectives. Those are the most important parts of the microscope. Those are the parts of the microscope that gathers the light, that collects the light. You don't have to buy the $20,000 objectives, but certainly don't go to the low-end objectives. When you get up, because objectives, their ability to gather more light, make them bright, is really, really important, especially when you get into fluorescence. You want something that picks up as much light as possible. Most of the objectives nowadays are your plan achromats. In other words, they're corrected for two things. They're corrected for color correction, color aberrations, and they're corrected for a flat field. When I looked at microscopes 30 years ago, they had the achromats, and those corrected for color, but some of the microscopes around the fringes had blurry. They've corrected for that with plan achromats in since then. Now they've even got the plan achromats, which are correct again for flat field and color aberrations, because remember, light bends differently with different wavelengths. From the blue to the red, you will have different bending, and though if you're not careful and don't get achromatic lenses, you might have color fringes around the specimen. But all the good microscopes now, these are good microscopes. You don't buy these. These aren't the Jason microscopes you get at Severus Merchandise or something like that. These are very expensive microscopes. But you can have some input on the objectives. I would certainly try to get a little bit better objectives, especially at the 40 and 63x level. A little bit more there will help you a lot in some of the very weak areas or weak light areas, especially in fluorescence. A lot of times you don't realize that sometimes these objectives are anywhere from $2,000 to $10,000 each, especially some of the better ones. Again, the objective is one of the most important parts of the microscope because that's what's gathering the light. That's where your resolution is gained. You don't get resolution in the oculars. You don't get resolution in other parts of the microscope. The resolution has two areas, the objective and the substage condenser. In this case, since you have the tube and the Leica microscope in there, the substage condenser is kind of out of the picture for LMD work. Now, if you're not using or you're just using it as a regular microscope, yes, the substage condenser becomes very important then as part of increasing your resolution. I know the substage condenser was something no one ever talked about when I was in school. It wasn't until I had a real microscopist teach me about microscopy that I realized the importance of the substage condenser and the objectives. Those are probably the two most important parts of the microscope as far as getting resolution. If you go to fluorescence, in the past or the olden days, the fluorescence was often done by running the fluorescent light up through the bottom of the microscope. Now, most of your fluorescence is epi-illumination or vertical illumination. So that's what this is a picture of, is how your fluorescent image comes through the slide or comes through the microscope. Most of them will come through the objective or adjacent to light paths around the outside of the objective. Here, what happens is you illuminate the sample with UV. I think this is about UVA, about 365 nanometers wavelength light source. This is your excitation wavelength. This is the wavelength of light that's going to hit the specimen or hit the fluorochromes in there. The fluorochromes are then energized. If you remember from your chemistry days, what would happen is the electron would be bounced up to a higher energy level with the energy going in there. And the electron moves to a higher energy state, and at some point it's going to drop back down to the ground state or back down to its original state, and when it does, it's going to emit a photon. Now, many things do this, but what's important about the fluorochromes that we're going to be using, or we use, is that that emitted energy is visible. And it's going to be at a longer wavelength than the excitation length. So now we can see the images. So what happens is we have the let's see if I can work this. The excitation energy is coming down here, going on to the specimen. It's then the specimen will be a fluorochrome, and you can have multiple fluorochromes in there, blue, red, green. That energy will then be picked up through the objective, and it goes up here to the bypass filter. The bypass filter, if y'all using the 3130s or something like that, the fluorescence is the same as what's going on there. It's just using different fluorochromes. And what you have is a filter that filters out the original excitation wavelengths. And that's what this bottom line is. Here's your filter cube. It's going to filter out the excitation wavelengths so you don't have that confusion in there and only allow the emitted wavelengths to come through. In this case, you see the blue and the green, or not the blue and the green and the red, and you see the objects in the vision of the ones that you allow. Now, you can have different types of bypass filters. You can have some that only let the green go through, only let the red go through, or only let the blue, or different colors, different wavelengths. Or you can have multiple bypass filters. I'm not sure exactly what they have here today or here for this week, what we're going to teach on, but you can have different types of bypass filters. You can have as much as triple bypass filters. Again, it goes back to the energetic electron, then drops back to its normal state and emits a photon. This is the visible color that you're seeing, or the visible wavelength. Bypass filters block the excitation wavelength. This is why on your 3130s and 310s and whatever, or 377s, that you don't have all the background noise, because all that excitation wavelength is being removed or being filtered out. Other terminology: resolution. This is the ability to distinguish 2 points as distinct and separate. And if you look at how you can determine resolution, it's about 1,000 times the numerical aperture. Numerical aperture is that angle. Briefly or simply, it's the angle of the aperture or the objective when it collects the light. They put some other formulas in there, like sine and 1/2 sine or something like that, to get the numerical aperture. That's what I was talking about on the better objectives. If you can get a little bit higher numerical aperture, you're going to get better resolution. Y'all are probably most familiar with resolution when you go out and buy your monitors for your computers. You get some real high resolution monitors and get some real nice fine print. When y'all look at your printers, would you get 1200 DPI or something like that so you can get some right stuff? Yeah, anyone ever go back to the days of the dot matrix printers when they had like 9 pins? 7 pins. Yeah, you get a little bit better resolution now with those different dots prints. And that's what's happening with resolution. If you look at this picture up here, you see the low resolution. You see that little mite or whatever it is, creature up there. And you see at low resolution, you don't see a lot of detail. You go to the higher resolution, you get a lot more detail. But remember, when I talked about magnification, if you don't have the resolution, magnification doesn't help you a lot. So if you look at this picture down here, that's obviously different magnification, but you're not seeing any more detail. So you can change the magnification all you want, but if you don't have the resolution, it doesn't help you. And that's what's called empty magnification. Empty magnification is when magnification exceeds the useful resolution. You ever go to any of the stores and see those microscopes that you can buy for about $100 and say, I can magnify 1,200 times on that microscope? It doesn't matter. You can magnify 1,200 times, but you're not going to see any better resolution than what you see with probably a hand magnifying lens or about a 10x objective. Because you can magnify a lot, but if you don't have the resolution, you're doing nothing. It's just empty magnification. That's the point at which you can look at it and see something there, but without that resolution, when you try to put it on a piece of film or take a picture of it, you're going to all of a sudden start blowing it up, and that's going to be it. Have y'all ever downloaded, like, take pictures off the internet and you try to make them up to big screen, and all of a sudden you start seeing these little squares in there? That's because you don't have the resolution. You can magnify it all you want, but pretty soon you're just seeing the big squares and nothing, no detail. And that's what we're talking about. That's where the objective is really important. It gives you the resolution. This is my soapbox about resolution and objectives and stuff, because I think a lot of people don't really understand, or they've probably never been told. It's not an understanding issue. It's just never been told about resolution and how important it is to microscopy. Just going out and buying a microscope and getting 5 objectives, and all the objectives cost $200 each. Well, you're back to the point, you get what you pay for. With this microscope, since you're already spending $100,000, $150,000, go ahead and spend the extra few dollars and get good objectives. You don't have to get the $20,000 objectives, and there are some $20,000 objectives out there. But don't be afraid to go a few $1,000s more, especially on the 40 and your upper end magnifications. One of the light sources or alternative light methods you can use is what's called differential interference contrast, or DIC. This is a method, or an optical method, creating relief, or like a 3D image effect on a sample which has little inherent contrast. This is a method of examining a sample without staining it. Or if you do stain it, it will actually give it a little bit more contrast to it. So it is kind of important. It is a kind of a complex method. You might think in terms of phase contrast, because most of the time when you go to school, they'll tell you about phase contrast and bacteria. Unfortunately, when you put that film on these slides, phase contrast, the ability to use phase contrast goes out the window. The Leica microscope does have DIC capabilities. I don't know if the ones they brought today has it. I think it does, but I'm not positive. Okay. And it may be, I wouldn't call it obligatory to get this, but it would be something you might want to consider, the ability to do a differential interference contrast, because it may help you when you are looking at a sample that's maybe unstained or very lightly stained. Especially some of the techniques that some advanced techniques I talk about may remove some of the staining, like the Christmas tree stain or something like that. Sometimes those are taken out by some of the techniques. And
I'm just curious, in this group, does anyone in your lab do sperm ID that's for unstained samples? Or that confident? Okay. Any of the labs here.
I used phase contrast for years. I loved it. I could look at wet mounts and everything with using phase contrast, and it's a very good optical staining technique. I love phase contrast. In fact, I like it better than the Christmas tree, but I don't do too much anymore with that. But this is a technique that's along those lines that you can use. Now, of course, wet mounts on the LMD are kind of like an anathema, oxymoron. You can't do it. You got to have a dried sample to cut. You can't use cover slips and things like that. So the phase contrast is out, but differential. Okay, you had a.
Well, I was going to say we did purchase a DIC at the North Louisiana Crime Lab for our Leica microscope, and a lot of it's just getting used to looking at the sperm without, the staining, because that's what we're used to. But I think it's just one of those things. It's a learning curve, and eventually you can get used to it. But part of what probably Christine's going to talk about tomorrow, and I'm a little bit today too, is the staining itself could affect downstream analysis. We want to make sure with the PCR and the DNA typing that we get the best possible results, peaks, good peak heights and whatnot. And I know Christine did a lot of studying of the staining and how it might affect, does it inhibit PCR, your peak heights, are they higher or lower? So that's one of the reasons why we bought the DIC, was from Christine's research. We thought, well, just in case, let's buy this DIC, so if we don't have to, we won't stain. But a lot of that, again, it's just a learning curve, at looking at the sperm that way.
But again, the DIC is an option. It's something to think about. It is a little bit more complex method of imaging. It gives you images. The 3D relief of the images with DIC might look like something like a scanning electron microscope, where you get the 3D relief image. The problem with the optical staining with DIC is that anything in there might give some type of relief. And unfortunately, the pen slides that we're using have little holes in them, which, like other people, are really trying to get work out. And these little holes can affect the image of the DIC microscope. And again, that's kind of my note at the bottom, is that you have to be careful what you're looking at with these images with the DIC, because it may just be a blemish in the membrane or something like that. But it is certainly a technique that is usable, and it may have some applications. Even the three of us that have been working with this, we're still somewhat in the infancy of laser microdissection. I think there's going to be a lot of new stuff coming out with it, new abilities, and with more people doing it, obviously there's going to be new things that are brought out, seen, and understood and developed. In fact, at the last week, I was talking with someone that might improve some of the procedures and stuff that we've used, especially for the fluorescence, the chromosome painting. You've probably all seen some type of image of the microscope. But what is happening with LMD? This is the Leica slide, but you see the laser beam coming through the objective is actually cutting there the sample and dropping it down. So when we go to the microscope, how does that really happen? What is the laser doing there? We can look at the slides, and everyone's really comfortable with looking at things, seeing things through the microscope. They actually believe what they see. It's all really there. But when we get to the lasers, some of the first questions I ask Andy Lee about this, okay, that laser, why is it not tearing up the sample too? Why is it not burning into the cell? Why this is a UV laser? Why is the UV not damaging the DNA? Is there bleed over? Is there material around the side? What is happening? Is it just melting it, or is it doing something else? And that's what I'm going to talk a little bit about today, how that laser is doing the cutting. If I can figure out. I don't want to end the slide. When in doubt, go to the keyboard. Okay. How do you get lasers? Well, how do you get laser light? This was a simple diagram my son sent me. And the N's and the E's are energy levels and periods of the periodic table. Y'all remember that from chemistry a long time ago, huh? People in the lab said, yeah, but I had that years ago. And I said, whatever you had years ago, I had it a lot longer than you did. Kelly's probably heard that more times than she wants to hear. Yeah, so, oh, I had that 10 years ago. Well, I had it 30 years ago. Okay. What is happening is basically in laser, what you do is you excite the electrons or excite the period in this. So over here, you get it excited to this stage. You may have some drop in energy, but here is your important lasing area. When this discrete energy drops from this point to this point, y'all do remember in chemistry you had the D shells, F shells, S and P? Well, when in every element, those are discrete energy levels. You can't drop, half a P or half a D. You have to go for the whole D down to the P or something like that. So those are discrete energy levels. And certain things laze really well because when they drop in that energy level, it gives off a particular wavelength that's important, one that you can see or one that puts energy into something. Carbon dioxide lasers, you may not see them. Argon lasers, you see a nice blue light. You also have multiple spectral lines because you can have different electrons drop to different energy levels. But why it is so coherent is that when you're lasing it or when it's dropping, all these same molecules are dropping the same energy or emitting the same energy at the same time in a very coherent fashion. Now, there might be a lot more detailed explanations of that, but that's what my son said. This is the simple method. So that's what I gave here. And of course, it can drop back down to the ground state where it's going to be re-excited again. Now what happens in pulse lasers is this emission is pulsed. You don't put all of the laser into a solid beam. I know if anyone's ever watched Goldfinger, they saw the laser trying to cut through the table. And of course, James Bond was laying on the table at the time, and he talked his way out of that. So, but now the new lasers, the ones that we're talking about now, don't have that solid beam. That was basically cutting by heat. Just putting energy in there until you were burning it. And if you remember James Bond, the 007 Goldfinger, it was actually had a little flame coming off the table. The new pulse lasers don't do their cutting by heat. There's a little bit of energy that goes into it in the heat, but really the heat is not the major component of the cutting. That's why when you're cutting that slide out or cutting that material out, you're not seeing flames coming off your slide or the plastic going into just poof, flaming up, because heat is not the main method of cutting. The main method of cutting is ablation. If we look at different types of lasers, pulse lasers and ablation, you've probably heard of ablative or ablation. If y'all remember the Apollo spacecraft. Y'all do that, huh? Y'all remember Apollo, Gemini, Mercury? I've already dated myself. Or the space shuttle now, that material on the bottom, those heat shields, those ablate. They get so hot they just go directly into the plasma. They don't melt or anything like that. That's basically what ablation is. You just get basically the element itself is just vaporizing without having to go through all these different stages like solid, liquid, and then gas. Ultrapulse lasers work by a multiphoton nonlinear process. What they do is that energy goes into there in a pulse form. Now, when you talk about lasers, you have 1 nanosecond, 4 nanosecond pulses. That's what we're talking about in these lasers. When they talk about ultra-fast, they're talking about picosecond pulses. And my son, what his work was done was femtosecond pulses. He was down to the 4 to 10 femtoseconds, which is 10 to the minus 15th second pulse. That's so fast that the molecules don't even have time to spread out the heat. It basically just hits them and goes out. Now, these nanosecond pulses are really right at the edge of that. And I'll get to that in the next slide. Photons of the ultrafast pulse laser are bunched at a very high density, and material absorbs several photons at once. And basically, they absorb them so fast they don't have time to transfer them. These pulses, when we go into the picosecond range, are faster than the vibration of the electron. I mean, of the element, of the crystals. So it's so fast they really don't have time to dissipate the heat. Unfortunately, in 1 nanosecond and more laser or higher, slower lasers, there is a little bit of heat transfer. But you can see the difference in a nanosecond laser up here. And here's your picosecond laser. Look at the difference. That's clean, flat ablation there. The other one, you see a little bit of melting effect. And what's nice about even the ones that have the nanosecond and the picosecond is they will work on transparent materials. So you don't have to have something. This can work on the elements or the atoms that are in the transparent material. You don't have to have just the colored objects or stains, something like that. It will work on plastics as well as other things. This is actually machining tools. Who knows, the way they have in the future, our new way of labeling evidence may be to put it under a little laser and they put a microscopic dot on there. You know, they're using lasers to label eggs now. They can have the date the eggs was picked or were collected and processed. They have them and they just write on the egg and with a little laser what the dates and types. They're using that for like micro labeling and stuff. So that's what my son's telling me. He says, "Y'all ever have to label anything?" Pulse lasers and ablation. And again, here we look at the one on over here is about the speed of the laser that we're looking at. We're looking at a 1 nanosecond laser with the Leica. and the older ones have a 4 nanosecond pulse. The time length is the length of the pulse. Then they go into hertz, is how many pulses per second there are. What you have is the laser beam comes through there, nanosecond laser pulse first heats the target. However, this heat is very, very brief, because once initially melting, then the next pulse comes through and basically evaporates all of the electrons, just wipes them out, converting that sample or those atoms into plasma. This happens so fast that there's very little time for the heat to spread out from the laser beam. So the picture that I've checked over here is what we're going to be looking at here. We do get a little bit of a melting, little bit of casting out, a little bit of debris coming out of there, and a very small HAZ, which is the heat affected zone. I can't tell you the exact heat affected zone because it's based upon the diameter of the beam, and the diameter of the beam is dependent upon which objective you're using. Always seem to go back to that objective. The higher the magnification objective, the smaller the beam. If they were ever able to go down to 1/10 nanosecond pulses, you can see the nice clean cut on the right-hand side. When you talk about 100 picoseconds, this pulse heats up the material, but it is so fast that it basically goes directly to plasma without any of the melting. And this is not long before, I think probably the 3rd generation will have this label of pulse lasers. Advantage of pulse lasers. Again, this is not a heating effect. If you had a solid beam going down through there, it would definitely have a melting effect. And that's not really what you want. You don't want heat around the edge. You want it to be, that material to be cut or ablated immediately without transferring heat to the side or heat affected zone. You want that to minimize that as much as possible. And the fast area lasers are a little bit greater than heat diffusion time. As you see, we're right on the edge with the lasers. If they could drop that pulse time just to maybe a 1/10 nanosecond or 100 picosecond, they could actually cut out that heat affected zone almost entirely. The pulse lasers that we're using now is just a little bit greater than that heat diffusion time. Again, it's just about half a nanosecond more. If they could just cut down a little bit, we would not have that. We would go directly to straight ablation. We are ablating, but there is a little bit of a melting effect or heat affected zone around there. Material briefly melts, then energy strips the electrons from the molecules, causing plasma. Nearly all of the energy of the pulse is used to plasma formation. No heating of the surrounding material, or actually it's minimal heating. Little debris or recast material, and little collateral damage because of the pulse laser. Again, if you went to a straight beam, you would have the heat and you'd have the problem. The pulse lasers are really neat on this. That's why you're looking at pulse lasers, because they can do that without making a gigantic heat affected zone around there. If we look at just a brief history of laser microdissection, and that's fairly brief history, again, it's relatively brief history for forensics, but well established in the medical field. This has been used, first occurrence of this was 1996. It's been used primarily in the medical field, especially if you want to pull out certain cells. If you want to go in there and just pull out, oftentimes when they take a tumor out of an individual or cancer cell, there's normal cells mixed in there. So if they want to look at the genetics of the cancer cell, they still have to look at the genetics of the whole biopsy or tissue sample they took. In this case, what they're doing with laser microdissection, they're going to say, okay, here's a tumor cell. I'm going to cut this out without any additional cells. And that's really neat. I mean, it's kind of great. I mean, it's kind of, if I had I wish I kind of had something like this for my dissertation. I was looking at pituitary cells, and I was looking at certain ones. the ones that produce growth hormone or the one that produce thyroid stimulating hormone. It would have been great to take a pituitary and just cut out the cells that I wanted to look at and see what their expression level was. And they're probably doing that now. I haven't checked back on it, but this is what the first use of the microscope was. Then I think Christine was the one that recognized its ability for forensics, probably because of her forensics background. And in 2003, 2004, she began working on this. And so really, it's only a couple of years into this that we've really had some work done on it. We've done some work at our laboratory, and I think it's really, really great stuff. I do believe that this is going to end up being really important in forensics, because so far everything that I envisioned or dreamed of with this has been doable. It can be better. There may be better techniques. You know, it's like everything else. But when we first started with PCR, we were starting with in the upper nanogram range, 1, 2, 3, 4 nanograms. Now we're working in the picogram range of DNA. I didn't do much RFLP work, but they started with the blood stain the size of a quarter and got it down to 50, 60 nanograms. And I think this work right now with the laser microdissection is in it so much as infancy that we're seeing that everything can be done now that we're thinking of. The only thing is, can we do it better? And that's where we're beginning to see right now. We're starting to work on, can we do it better? And with a lot more people working in the field, that's what we're going to see, things working better. They're working now. They're doable now. We see that they're doable. Once they're doable, then a lot of minds get involved and say, okay, let's do it better. And that's part of what this technology transfer workshop is let's get some more people thinking about it, and somewhere along the line, people are going to think about ways of doing it better, improving it. And that's what all this is about. I think that's what Carl was saying here. You know, more minds on a problem, the quicker it's going to be solved, the better it's going to be. If we look at the types of the LMD microscopes, I got a couple of responses back. I know there's several types out there. I'm only covering really 2 right here. But I know some people may have a little bit different types. The Leica microscope is automated. I'm still used to using the coarse and fine microscope controls. That's gone now. So I get mixed up and I'll turn different knobs and it'll move the stage around instead of focusing up and down and stuff. So it is much more of an automated microscope. You don't have to deal with going up and hand changing your objectives and going through there and flipping the knobs for your bright field and fluorescence. A lot of that's so automated now. You just push a button on the screen. I'm still a little bit more manually oriented than I've never used Xboxes or anything like that, so I'm not much of a gaming person, but these microscopes are a lot of fun to work with. Very interesting. It does have bright field, fluorescent, alternative optics. Yes, this microscope does have phase contrast, but our capabilities you can put on it, but it really is not very helpful with the pen slides we have. The slides have to have a film coating. I think some of the other microscopes can use existing slides or glass slides. Some of the ones that have little sticky pads that pick up stuff can use the things like that. Or I think there's some that melt plastic on there. So there are some microscopes, laser capture or laser microdissection scopes, that can use existing slides. The Leica cannot. All the work has to be done on a film-coated slide. That has advantages, that has disadvantages. You can't go back to your slides from 5 years ago and try to pick out the sperm. I think there are some microscopes out there that can, though. The laser cuts the plastic film using the ablation, the pulse laser, allows the cell samples to drop into a tube, and you can put up to 4 different tubes on there. There may even actually be some strips that we can do more. I'm not positive, but an 8 strip sample.
Yeah, I think 8 in the new instrument.
Yeah.
Well, I know with the old one, the one that we have, there's an 8-tube strip. However, they're more like an assay plate kind of tubes.
Mm-hmm.
So as far as being able to take them and stick them in a thermal cycle, you can't.
Yeah.
But I'm not quite familiar with the new one, what the tubes are like.
I think I was told, I think the new ones are 8. But we can, when we
Are
go
they
into
PCR tubes?
I think so.
Okay.
When we go into the lab, we can ask Andy Lee, so he knows all the technical.
Well, I know they made ours for our tubes, for our PCR tubes. They have some standard ones for regular PCR tubes, but they actually made ours. We sent some of our PCR tubes to them, and they made them specifically for those tubes. So they're out there. They can make. I'm sure they could to machine them for strips also. Whatever you had, they could work with that to get it to work. UV laser does the cutting. The wavelength is for the diode lasers about 355 nanometers. The new lasers are a diode laser. We have a gas laser. The 4000, which I think Christine and us, that's what we have, is the gas laser, cuts at 337 nanometers. And the laser beam, as you saw in the initial cartoon or initial video, cuts through the objective. It's really neat in that it's done by prisms. The beam is directed by prisms. I didn't know that till recently. I asked my son, I say, how do they work these beams? He says, well, they can either do a galvanometer, like your gas gauge on your car, or they can do the modern way through prisms. And I found out that this is a very novel way, not novel, but it's certainly a patented way by Leica of doing it with prisms. I believe the other microscopes actually move the stage to do their cutting and not run the laser through the objective. I kind of like the idea of going through the objective. I think you can get a lot better control of it through there, especially the size-wise, but I'm sure the other microscopes have their advantages by doing it through the stage. But it is neat that this can be done through objectives. Or through the objective. See, again, that objective keeps coming back. Most important part of the microscope. Everything goes through it. The laser capture detection microscopes, or dissection microscopes, the one I got information on, the one that they sent me back information on, molecular machines and industries, the cell cut, samples collected on a sticky cap. They say this has advantages in the fact that you can look at that cap and see what samples are on there. The stage, I believe, was moved. The sample can be easily inspected after cutting. The Leica can be inspected. We can look at it and see if they've been inspected. But MMI says that theirs is actually good enough to where you can actually count. If you said you collected 50 cells, you can count 50 cells on that cap. And that certainly has some advantages. Some of the work that we've done with the microscope says, okay, we're not always 100% certain that sperm cell or epithelial cell is dropped into the sample tube or dropped into the collection. And if there was a little bit better way, you can look at it and say, okay, yeah, I see some down there, but I can't really count them. This one, they say they can actually look at it and count them. Pulse laser cuts through by moving the stage, and they also report this as contamination free. In other words, you just pick up the one that's been cut. I have anecdotally heard a little bit different about that. I'm not certain. There always seems to be this issue of contamination. If you're going to use a sticky pad, and did everything get off the pad, or did you pick up more than you thought you would, maybe a loose cell? When you do have these film-coated slides, those samples don't always stick to them too well. Some of the film coatings we've looked at, I don't know, when I was talking with Jackie about that ETC slide, I think some of the cells that aren't sticking on there are very well. So there may be an issue of how fixed the cells are to the plastic film. Again, this is some of the new stuff we're just now getting to or seeing about when we're doing this microscopy. It's something you certainly would have to look at in your own laboratory. Yes?
Just to mention that, this is my understanding on the cell cut, and I'd have to verify this, but you were talking about the sticky thing coming down and perhaps picking up maybe some non-specific cells by accident. My understanding is when I saw a demo of that is that they do something where they flip the slide or the membrane, and you're actually cutting from the opposite side, not where your smear is from. So the sticky cap is coming on top of the membrane that doesn't have the actual smear on.
Okay.
Yeah, so I think that it just tries to address that.
Okay.
It's like the opposite side.
Yeah, I believe they do some kind of flipping or sandwiching
Okay.
of the specimen.
again, that's probably goes back to contamination-free reporting. Because some of them, I think, there are other different types of sticky caps, and I think there's one microscope that has with electrostatic jumping or cutting where it pops the sample out of there. I think that one's one of the ones that can be used with the older slides, older glass slides or something like that. That's pretty much that on the basic microscopy and laser and things like that. Any questions?
Are these sticky caps autoclavable, do we know?
As far as the MMR.
Yes.
I don't know.
I don't know. I'm just wondering.
That's not something I know. We do have a contact as far as the MMI. I'm sure if you were to contact, find out a rep in your area or whatever, they should be able to give you more information as far as, you know, things like that. Your disposables or, you know, what's the word I'm looking for? Things that come with the microscope. Yeah, consumables. Yeah, that'd probably be something they can give you more information about because we don't have this microscope. We don't have a lot of experience, you know, with it. It's just at like an academy meeting. Sometimes we can go and, you know, they have booths like that at like Academy, the American Academy meeting and Promega, and a lot of times they have the instrument right there, and those would be definitely you should write down questions you have. But yeah, we have a contact because this guy gave us a lot of. He even gave us a couple PowerPoints, I think. So you should be able to get more information.
The details on the microscope. The details that we get come from the salesperson. So they're trying to sell it. And plus they're not getting us a lot of details because they know we already have another microscope. So they're not going to be as nice to us as they will be to someone that's looking to buy a microscope. And you can get other information from them. And I hate to say the best way to get the detailed information is actually have the microscope and work with it. I mean, we can tell you a little bit more about the Leica because that's what we're used to using. People that have used other microscopes may have have a different background or different experience level with those, and they may be able to tell you pluses and minuses. I mean, we can tell you pluses and minuses about the Leica, and of course we think it's really great because that's what we have.
I was going to say, I think I may be incorrect, but I think California Department of Justice has an MMI. Do you know this, Pat? Or
I know they purchased the Palm.
Did they purchase the Palm?
I know, at least they were in talks to purchase the Palm. I think when I saw them at Promega, they were still deciding, but I think they were one of the Palm accounts.
I thought someone had bought the MMI.
They may have bought that too.
I can't remember.
Maybe they've got them at least in-house and trying them.
And that would be in Richmond, that lab? Do you know which lab?
I think so. I think that's right.
I just want to mention, just so that you can write it down if you'd like, the two other major systems that weren't mentioned today. The first one originally was called Arcturus. I think it's been bought up by another company, but I think they may still use the Arcturus label.
Yeah. Veritas.
It's Veritas now.
The newest version of it.
The newest version.
Arcturus is still what they're.
And the main, because there's each different system has a different way of collecting the sample. That particular system uses regular glass slides, and instead they use a cap that has a membrane on it. And that membrane they use to kind of almost lay on top of the sample, and they use the laser to melt the plastic onto your cells or tissue and basically pull it off the slide. That's the difference on the Arcturus system. And then the Palm system, the way that works is similar in a way to Leica in terms of it uses a coated slide. But what happens is that the sample is basically catapulted from the slide into a cup upwards, as opposed to Leica uses a cutting method and drops the sample down into a tube. So those are kind of the main differences between the instruments.
I was going to say, for those of you who don't have a microscope and you're thinking of purchasing one, it really would probably benefit you to try to talk to other labs that have different microscopes if you can find us, because like Pat was saying, a salesperson's going to, give you their strong points about that microscope. That's what they do. That's what they have to do for their company. So it may help to talk to some, if we can try to get information about the other labs. I know there's a few, that have Palm. and the MMI, Leica, and I'm not sure how many have the Arcturus. I know New York City does. I think some European labs maybe do, but I think it would benefit you before you buy a microscope to try to get as much information you can about the different microscopes so you could see maybe how in your laboratory one might work better over the other.
Have you experienced any problems with the HAZ or heat affected zone? Is that adverse effects on that?
I haven't seen any.
It's so minimal.
Mm-hmm. You can spread it. You can open up. You just basically draw a circle where you're cutting, so you can avoid the area a lot.
Okay.
And you can see what you've cut. You can look at the size of the beam as it cuts around there. So I don't think we've seen any problems with that. At least not knowingly. We've gotten results from it, so apparently it's not zapping it too badly.
Well, I remember that when Andy first showed it to us. That was my first thought. I thought, okay, there's a laser, cutting. Is it, and it's UV? Is it going to just destroy the DNA? And of course, initial research, it took us a while to kind of, okay, is this working or how's it going to work? But yeah, we're getting results now. So I don't, and like you said, you're cutting a bigger, with the light anyway, you're cutting a big circle around your area, and you'll see this in the lab. And so, I think unless you're cutting right around that sperm head or right on, on your nucleus, I think for the most part, it's not doing anything to it.
Is that a problem then if you have a really heavy slide of picking up other cells then too?
I'm sorry, what?
If you have a really heavy slide with lots of epithelial cells, is that a problem then picking up other cells then too?
Right, so you're talking about like when sometimes you have a vaginal swab that's
right.
just thick with epithelial cells. Well, that's part of this, again, we're sort of in the infancy, is trying to get the best way of either making a smear so those cells really spread out, or some type of spotting technique. That's part of what our research has been. I think Christine and mine.
A little bit about it.
Right, because I remember actually when I was at the meeting that she first spoke, that was one of my first questions. What happens if you've got this heavily populated epithelial cell, spot? You see sperm, but they're all collected on the cells themselves.
Right.
Yeah, that's one of the sort of disadvantages is when you have this really heavily populated epithelial cell sample, is trying to cut those sperm. So yeah, that's something.
It's going to be an interesting concept when you get to things like sperm paint or fluorescent identification of sperm, because you can actually see the sperm that are stuck on the cell membranes,
right,
or under the cells,
right.
where you can't see those normally. You now have the capabilities with the fluorescent identification to see the sperm that are stuck on the membrane or stuck under a cell. So that's going to be an interesting concept of, are you going to cut, what are you going to do? I mean, you could line the laser up and zap the nucleus and then go ahead and cut out the sperm or something like that. I mean, there's different ways of approaching this problem, but it's going to be an issue even without clumps of cells, because if you've got a cell sitting on a spermatozoa sitting on top of a cell membrane, or theoretically sitting on the nucleus of another cell, how are you going to do that? What are you going to have? What's your point on that?
Well, I do have to say, generally, if you do have a sample that has a good number of sperm, usually just by even just a spotting technique, and I'm sure you guys have seen this if you're looking at your spot under a microscope, a lot of those sperm migrate out to the side of the spot. So a lot of times, especially with Christine, gosh, she's done a lot of really low copy number. I mean, you usually can find sperm free of epithelial cells. But definitely what you're speaking of, there's probably still going to be a little bit of that issue.
Yeah, I've noticed also they do have an affinity for cells. So that's the
Yeah,
problem
they do.
They're attracted to other cells.
Yeah.
So you just see a clump of them around an epithelial. So.
But that's the great thing about the low copy number studies is hopefully if you did have a heavily populated epithelial cell sample, there would be enough sperm that were free of the epithelial cells you could cut and go. So hopefully that won't be an issue. But again, that's something that has to be worked on a little bit, I think, in your lab.